In this video, we will discuss a few problems associated with the calculation of electric potential energy of point charge systems. Problem 1. Suppose three charges, all with positive charge at magnitude 1 microcoulomb and mass 2 times 10 to the power minus 10 kg, lie on the x-axis as shown. So Q1, Q2, Q3, and they are separated by distance r, where r is 2 centimeters. And they are all held fixed in place. Assume Q3 is then released. Find the speed of Q3 when it gets to infinity. So this problem involves conservation of mechanical energy, in which the mechanical energy of the system is conserved before and after. So before, or the initial state, is as shown. After, or the final state, is where the two charges are still, Q1 and Q2 are still as before. So that is Q1 and that is Q2, separated by distance r. And Q3 is at some infinite distance from these two charges, and it is moving with some speed v, and that is the speed that we want to determine. So the mechanical energy for the initial state is the initial potential energy, initial electric potential energy, plus the initial kinetic energy of the system. Now the initial kinetic energy of the system is 0 because none of the charges are moving. They are held in place. So all we have to do is to determine U sub I. U sub I is the electric potential energy of this system of the initial configuration, and that can be calculated in the following manner. So let's look at pair by pair. The first pair is Q1 and Q2. So that's Q1 times Q2. Each has a charge of 1 microcoulomb. So 1 microcoulomb times 1 microcoulomb is 10 to the power minus 12. The distance between them is r. So r is 2 cm, 0.02 meter. So that's the first combination. The second combination is Q2 and Q3. The product of the charges is still 10 to the power minus 12. Each contributes 1 microcoulomb. The separation distance is again 0.02 meter. The final pair is 1 and 3. So 10 to the power minus 12 over 4 cm, so 0.04 meter. Remember, K is a constant, 9 times 10 to the power 9 in SI units. Now let's look at the final state. The final state, the total mechanical energy, is the final electrical potential energy of the system plus the final kinetic energy of the system. The final kinetic energy of the system is due to only Q3, because only Q3 is moving. Q1 and Q2 is not moving, it is held in place. So the kinetic energy is half. The mass of the system is 2 times 10 to the power minus 10 kg, it's right there, it's given, times the square of the speed that we want to determine. The final electric potential energy of the system is contributed by only these two charges, that 1-2 pair. Q3 does not contribute because it is at an infinite distance, so any term would involve the value of r approaching infinity. So any potential energy term with infinite distance would simply be 0. So U sub F for the final state is quite simply K. The product of Q1 and Q2 is 10 to the power minus 12. The distance between them is r, so r is 2 cm or 0.02 meter. So U sub F plus U plus K sub F will give you the total energy of the final state. Equating this term to that term due to conservation of mechanical energy, one can solve for the final speed of charge Q3 at infinity. And solving for V, we get V equals 82,158 meter per second as the answer. And that solves the problem. Problem 2. A positive charge with magnitude 2 microcoulomb, mass is 1.6 times 10 to the power minus 10 kg, is released at x equals to minus 1 cm in a region with constant electric field with magnitude 1000 Newton per coulomb. The field is in the positive x direction as well. Determine the speed of the charge when it gets to x equals to 4 cm. So let's assume that's the x-axis, that is the origin of the x-axis. So the positive charge is at the position x equals to minus 1. So right there. So this is where the positive charge is. The magnitude or the strength of that positive charge is 2 microcoulomb. Since the electric field is also along the x-axis, so that is the direction of the electric field, and we can write its expression as 1000 I hat Newton per coulomb. So what's going to happen to this charge? It's going to move all the way to the right following the direction of the electric field. The question is, what is the speed of the charge when it gets to x equals to 4? What is the speed there? Note that all the length is measured in the units of centimeters. So x equals to minus 1 is the initial point. X equals to 4 is the final point. So we are going to use the work kinetic energy theorem to solve this problem. The work being done on this 2 microcoulomb charge is due to this electric field. So it creates an electric force with a magnitude Q times E, and in doing so it is displacing the charge a distance of 5 centimeters. So let's call that displacement delta x. So the work is therefore Q, which is the strength of the charge, 2 microcoulomb. Electric field, the magnitude of the electric field is 1000, and the displacement is 5 cm, so 5 times 10 to the power minus 2. And this work is quantified in the units of joules. Now the work that we have just computed according to work kinetic energy theorem is equivalent to the change in kinetic energy. The change in kinetic energy is the final kinetic energy of the charge minus the initial kinetic energy of the charge. The initial kinetic energy of the charge is 0 because the charge was at rest at this point, the initial point right there. The final kinetic energy of the charge, namely the kinetic energy of the charge when it gets to x equals to 4, is given by half the mass of the charge, which we know, 1.6 times 10 to the power minus 10 kg, it's given right there, times the square of the speed that we want to compute. Note that the kinetic energy is actually increasing because the charge is speeding up in that direction. And this is due to the positive work being done on the charge. So how do we know the work is positive? The electric force is in this direction to the right. The displacement is also in that direction, so the dot product of the force vector and the displacement vector is positive. So work is positive, and the change in kinetic energy is also positive. So namely, the final kinetic energy is greater than the initial kinetic energy. Now equating these two terms, we can solve for the unknown v. And you get the speed to be 1,118 meter per second as the speed of the charge when it gets to x equals to 4 cm. And that solves the problem. Problem 3. A proton has an initial speed of 10 to the power 6 meter per second as it enters a region of constant electric field. The region is 6 cm long. What is the potential difference in the region if the proton exits the electric field region with a speed of 2 times 10 to the power 6 meter per second? And also find the magnitude of that constant electric field. So this is the region where you have this electric field. like that. And this is the initial point, and that is the final point, let's say. At the initial point, the speed of the proton is 10 to the power 6 meter per second. And when it gets out of the region, it's 2 times 10 to the power 6 meter per second. So the length of this region is 6 centimeters. Now we know since the proton is moving from the initial point to the final point, these 2 points must be at different potential, with the initial potential greater than the final potential. Otherwise, the positive charge would not move like that. So the positive charge would always move from a region or from a point with higher potential to a point with a lower potential. Now, since the system is conservative, the change in kinetic energy of the system is minus the change in electric potential energy of the system. The change in the electric potential energy is quite simply the magnitude of the charge times the change in the electric potential. Now, the change in electric potential is given by the final potential minus the initial potential. So let's determine the change in kinetic energy. The final kinetic energy minus the initial kinetic energy. So that is half times the mass of the proton. The mass of the proton is 1.67 times 10 to the power minus 27 kg. The final speed is 2 million meter per second. So you have to square that, 2 times 10 to the power 6 squared, minus the initial speed, which is 10 to the power 6. And don't forget to square that, you're computing kinetic energy. And you have to equate that to minus the strength of the charge. This is a proton, so the charge is 1.602 times 10 to the power minus 19 coulomb times the change in potential, or potential difference between the initial and the final point. Note that we know everything in this expression except for delta V, and that can be computed. And when you calculate the potential difference, you get minus 15,637 volt. Note it is a minus number because the change in potential difference, the change in potential rather, is the final potential minus the initial potential, and because the final potential is less than the initial potential, it results in a negative number. Part B, the magnitude of the electric field. Now we know the magnitude of the electric field is related to the change in potential or potential difference in a following manner. The potential difference over the distance between the 2 potential points. So in this case, note we are computing magnitude right there. So the magnitude of the electric field is the magnitude of the potential difference, which is in this case 15,637 volts, over the distance is 6 centimeters, so 0.06 meter. And that's going to give you 2.6 times 10 to the power 5 Newton per coulomb, or another unit for potential for electric field is volt per meter. And that solves the problem. Thank you for watching.